Welcome to NimConf 2021. I'm Andreas Rumpf, NIM's BDFL, and I'm very proud to present you the following talks. We will start with a talk of mine called Zen of NIM. It's about NIM's design philosophies and how we should evolve the language further, what principles are behind NIM, but it's also an introduction into NIM, so if you are still unfamiliar with the language, after my talk you will be able to read NIM code snippets and understand what it is about. Then Chess Inbox will talk about how to make a platformer in Nico with NIM. So it's a framework for making simple 2D games. Then Peter Longo will share his NIM adventures with NimIp, which is a template-based DSL for publishing NIM code and combining it with pictures and images. For tutorials and blogs. It's inspired by Jupyter and R Markdown. And finally, in this first block of talks, Shuhei Nogawa will tell us about Nikoru, development container runtime in NIM. So yeah, this is about management and the runtime of container software. Then we will have a coffee break, and then in the second block of talks, we'll start with Peter Munch-Ellingson's talk, Why I Wrote My Own Keyboard Firmware in NIM. Yeah, I think the title says it all. Followed by Torrentinim, Building a Torrent Crawler with NIM by Sergio Tapia. And last but not least, Mami Ratzimbazzafi will talk about his work at Status using NIM in production and why your company should use NIM in production too. Then we'll have a long lunch break. I think it's 1 hour. And then the next block of talks starts with Dimscord, to interact with the Discord API using NIM. So this is about how to write Discord bots via NIM by an unknown author. Followed by NIM in a real-time operating system world by Jeremy Creechley. So this is about using NIM in an embedded development setting. And finally, Norm, Where Are We, Where Are We Going by Konstantin Mokhalnov. It's a framework for dealing with databases. Then we will have a coffee break. And finally, in the last block of talks, Fabio Chevasco will talk about how to implement a programming language with NIM. His language is called Min. I think it's a stack-based programming language, so probably simple enough for others to understand. Then we will learn how to make music with Paramidi and ANSI by Zach Okies. Followed by creating a 3D game in Anu 0.2 by Scott Waden. So this is a framework for making 3D games. And finally, we will learn about the new Pixie library. It's a full-featured 2D graphics library for NIM. Andre van Hauk will explain to us how it works and why you should choose it over Cairo or Skia, for instance. So I want to thank these authors very, very much for contributing their talks to this conference. Without their help, this wouldn't be possible. And now it's time for the first talk. Hello and welcome to my talk, Zen of NIM. I'm Andreas Rumpf, the lead developer and primary inventor of the NIM programming language, and still it's BDFL. So Zen of NIM, in this talk I will explain the philosophy behind the language and why it is that NIM is so useful for these wide range of application domains that we are seeing. So Zen means we will arrive at a set of rules that guide the language's design and evolution. But I will go through these rules via examples, and so at the very end I will summarize what we have accomplished. So the very last slide is the most important one in this talk. Okay, so I think we will see in this conference once again that NIM is widely applicable to a wide range of application domains, such as scientific computing, games development, compilers, operating system development, scripting, and everything else. And I hope to explain why that is. But first, let me introduce NIM via its syntax. So I'm aware that most of you probably already know the language, but to give you a gentle introduction into NIM, even if you haven't seen it before, I will explain the basic syntax and also come to interesting conclusions. So NIM uses the indentation-based syntax and as inspired by Haskell or Python. Yet it does fit NIM's macro system. So we start with expressions. So NIM distinguishes between statements and expressions, and most of the time the expression is just function application or procedure call or whatever you want to call it. So, and we use the traditional mathy syntax with parentheses. F without arguments is called, so the call to f without arguments is done with the parentheses. If you have one argument, then it's f of a. If you have two arguments, it's f a comma b. And then there's sugar to write the same thing. So here in rules 1 and 2, I outlined that you can leave out the parentheses, and there are examples for so that you can see why that might be useful. For instance, if I have a spawn lock some message call, which is a nested call, the spawn kind of looks like a keyword, which is a good thing in this case because it does something special. Echo hello world is also famous for leaving out the parentheses, because usually you write these statements for debugging, and then thus you are in a hurry of getting things done. You have dot notation available, so a dot f is the same as f of a, and again you can leave out parentheses or not, even with the dot call. So these are rules 3 to 6. Rule 7 is about string literals. So if you have the f followed by a string literal without white space in between, it turns the call, it's still a call, but the string literal is turned into a raw string literal, which is very handy here for regular expressions, because regular expressions have their own idea of what the backslash is supposed to mean. And finally, in the last line, we can see that you can that you can pass a block of code to the f via this :b syntax. And also this code block is usually the last argument that you pass to the f. And this can be used to create custom lock statements, which surround the echo high via a lock statement. There is one exception. I mean, you can leave out the parentheses unless you refer to the f directly, and then you want the f to be the f itself and not a call to f. As you can see, like if you say myArray.map of f, then you don't want to invoke f and pass f's result to the map, but instead you want to pass the f itself to the map, and that's why this special case here was made. NIM has operators, and sorry, I'll make this a little bit smaller so that you can still read it. So you have binary operators and unary operators, and usually you write them as x add y, and the add could be plus or multiplication or whatever. And unary operators as add of x, for instance, unary minus. But there is no explicit distinction between operators and functions, or binary and unary operators. So here I have an example of a function which I named ++, and since a ++ is an operator token, I have to put it into backticks. And what ++ does is something weird. So it takes an x of var int, which means it's mutable. so you can modify it. And it takes two optional arguments, y, which defaults to the value 1, and z, which defaults to the value 0. And then we add these numbers up and store the result back into the x. So now if I have a variable g of value 70, I can say plus plus g. So I invoke the plus plus as the unary with the unary operator syntax. I can say, and then the default arguments would be picked. Or I can pass the 7 to the y and via this infix notation. So g plus plus 7 means pass g to x, 7 to y, and 0 to z. And finally, if I want to pass 3 arguments to a binary operator, that's still possible because I can use an operator just like an ordinary identifier, which is done in line 8. So g dot, and then in backticks plus plus 10, 20 passes 10 to the y and 20 to the x. And finally, if we print out the result, it would be 108. Okay, and once again, this var keyword here indicates mutability. All other parameters that I pass to this function are immutable. So as I said, we still have this statements versus expressions paradigm. And statements are built up by requiring indentation. You don't need indentation for simple statements like an assignment. You need the indentation when it's otherwise too messy. So for a nested if statement, so that we know that the else belongs to the outer if statement, we use the indentation to figure this out. And finally, if you have more than one statement, you need the indentation to split these up via new line then, or you can also use a semicolon between these, but this is very uncommon in Nim. Expressions are not really based on indentation, so you are free to use additional white space within expressions. This can be very handy for breaking up long lines. And as a rule of thumb, you can have optional indentation after operators, symbols, parentheses, and commas. And finally, if and case, the if and case statements are also available as expressions and so can produce a value. So here I have a simple example. And this is a full Nim program this time. And so to show a little bit more of Nim syntax. So if you are familiar with Python, this should be straightforward to read. Nim uses static typing, so the parameters have types attached. So as the input parameter named s has the type string, x has the type set of character, and this function in called index of produces an integer value as the final result. And the example shows that, yes, okay, so you can iterate over a string, or rather over its indexes via this for loop. And the goal is to find the position of the character inside the string that matches the set of values. So in this index of line, there is a set construction. We can construct the set of white space via these curly parentheses, containing space and the tabulator symbol. Okay. So our first rule in our Zen of Nim task is concise code is not in conflict with readability, it enables readability. And so as you could already see on this tiny example, that it's very easy to follow, it's very easy to read, and because we basically leave out the symbols that carry little meaning, such as curlies for blocks or semicolons to terminate a statement. And this scales up. So in longer programs, it's really helpful when you have less code to look at, because then you can more easily figure out how the code is supposed to work, or what it can do, without getting too much details. So usually the argument is like, oh, this syntax is terse, so it's unreadable, and all you want to do is to save typing work, which in my case totally misses the point. It's not about saving keystrokes or saving typing effort. It's saving the effort when you look at the resulting code. So yes, programs are read maybe way more often than they are written, but if you read them, it really helps when they are shorter. Second rule would be the compiler must be able to reason about the code. So we want structured programming, we want static typing, we want static binding, we want side effects tracking, exception tracking, mutability restrictions, because in my opinion, so the enemy is shared mutable state, but you can, if the state isn't shared, it's fine, really fine to mutate it. So we want to be able to do this precisely. And finally, value-based data types, because aliasing is very hard to reason about. And we will see what these points mean in detail now. So here I have an example. The task is to count all the words in the file that is given via file name as a string. And it produces a count table of strings. So in the end, there would be entries for every word, how often it occurs in the text. And so thankfully the NIM standard library already offers us this count table, so it's very, very easy to do. We start with line 5. Result is this new count table, and result is built into NIM and represents the return value. So you don't have to write return result, which is unstructured programming, because return immediately leaves every scope and returns back the result. So this is why, I mean, NIM does offer the return statement, we've already seen it, but we advise you to avoid it for this reason. Okay, and then we read the file line, I think, completely into a single buffer, and then we call split to get at the single word, and then we count the word with via result inc to count this word in line 7. So once again, structured programming, what does that mean? It means that you have a single entry point into a block of code and a single leaving point. And here with this continue keyword, I leave the for loop body in a more convoluted manner, let's say. Why is that? Because look at this code. So for every item in this collection, if the item is bad, oh no, continue already, and then after otherwise, we use this item. So what do I need? What do I know in line 5? Well, I know that the item is not bad. So, but why not write this then, right? Here we use structured programming, so the indentation gives us clues about the invariants in our code, and so we can see much more easily that in line 5 the invariant holds that the item is not bad. So yeah, but look, if you prefer the continue and the return statement, it's still it's not a crime to use them. I use them myself if nothing else works as well, but you should avoid it. And more importantly, it means that we will probably never add a more general go-to statement to the NIM programming language, because it's even more against the structured programming paradigm. And we want to be in this position where we can prove more and more properties about your code, and structured programming really makes that much easier for a proof engine to help with this. And I think I need to, sorry, make this more readable, or at least so that you can read it at all. Okay, another example for static typing is that we really want you to use custom types dedicated to the problem domain. So here I have a little example showing you the distinct string feature. So we say nim code is actually can be stored in a string, but it's a distinct string. So it's a special type with special rules. And then in line 9, I have a proc that can run arbitrary nim code that you pass to it, but it's a virtual machine that can run the code and it can restrict what is possible. So there is a sandbox environment in this example. And there are custom properties that you might want to use. So for instance, you can say, okay, allow the nimcast operation, or allow the function foreign interface that nim offers. And finally, allow that the nim code to run into infinite loops. And then you can, this is an ordinary enum, but then you can produce a set of it in line 9, and indicating that yes, every option is kind of independent of every other option. And now if you compare this to C, for instance, where it's common to do this as well, you lose this type safety. Like in line 5, there's only like, okay, it's an unsigned integer, and nobody stops you from passing the value 700 to this function, even though it doesn't make any sense. And and you need to use these bit twiddling operations here to define allow cast and allow infinite loops. So you lose information here, even though it's very much in the programmer's head of what is really a valid value for this flags argument. Yet it's not written down in the program, and so the compiler cannot really help you. We want nim to use static binding. Here I modified the echo hello world example a little bit so that it says hello world 99. And what happens is that the compiler rewrites the statement to echo, and then you pass in brackets, this is an array of strings, and everything is turned into a string via this dollar operator. So in the end, it is a variable list of arguments of type string that is passed to the echo proc, and then can put the result to standard out. So, and we use here the overloading aspect of we overload the dollar operator for the types that we think can be turned into a string. And so it uses static binding for these dollars, no dynamic binding, as would be done in say, for instance, C#. And yet the mechanism is still extensible. So here I have my custom type, my object. I say, hey, the dollar operation actually is just the S field of this X. And then I construct an object with the value X, Y, Z. And echo understands how to echo the objects of type my object, because these have a dollar operator defined for them. We want value-based data types so that the program becomes easier to reason about. I've already said we want to restrict this shared mutable state, but one aspect, like one solution that's usually overlooked by functional programming languages, is that to do that you want to restrict aliasing and not so much the mutation, because the mutation is very direct and convenient and efficient. So here I define a type rectangle. It is an object. It has fields X, Y, W, and H. You can construct these then via this construction syntax. There is field access with the dot, very, very common among programming languages. And finally, the most important thing, assignment does copy in this case. So here I declare a variable other, and it should be the same as R. But then I mutate the other, the X field, to be the value 10. And we do know in line 14 that r.x is still 12 because the assignment performed a copy for us. So there is no spooky action at a distance involved here. There is only one access path to r.x, which is r.x, and other.x is not an access path to the same memory location. We want to be able to track side effects. So here I have an example. The goal is to count the number of substrings inside the S. And I start with, okay, result is 0. So first of all, there is no substring in S. Let's assume that. And then we iterate over the string, and find gives us a position of where the substring occurred. Unless it's negative, then we break out of the loop. And but let's assume this is in not correct code. So there is a debug echo statement why I is of value I. And the compiler would complain, look, you say proc has no side effects, but echo produces a side effect. So you're wrong, go fix your code. And the other aspect of Nim is the compiler is very smart and can help you. However, sometimes you need to get work done, and you must be able to override these very good defaults. So if I say, hey, okay, I know this produces a side effect, but I don't care because this is only code I added for debugging. You can say, hey, cast this body of code to a no side effect effect. And then the compiler is happy and say, oh yeah, okay, so you cast it. Go ahead. Cast means hey, I know what I'm doing. Leave me alone. We want exception tracking. Here I have my main proc, and I say, yes, I want races, nothing. I want to be able to ensure that I handled every exception that can happen. And the compiler would complain and say, look, no, this is wrong. Copy dir can raise an unlisted exception, namely this OS error. Okay, so you say, fine, in fact, I didn't handle it, but now I can claim, actually, yes, main does raise operating system error. And the compiler says, yes, you're right. We want to be able to parameterize over this a little bit. So here I have a generic proc x. So this in brackets, this e is a generic type. And I say, whatever e you pass to this x, this is what I'm going to raise. And then I instantiate this x with this value error exception, and I can catch it, and the compiler is happy. So I was really surprised to see that this works out of the box. I mean, I came up with this example and was quite sure that the compiler would produce a bug, but it's already handling this situation very well. And I think the reason for that is that somebody else helped me out and fixed this bug. Okay, mutability restrictions. Here I'm going to show and explain what this experimental strict funcs call does. So I have a node type, it's a ref object, so now I have a pointer to these objects. And next and previous are these usually, like it's a doubly linked list, right? And there is the data field of type string. And I say I have a function and the length, and it counts the number of nodes that are in my linked list. So pretty straightforward. Unless it's nil, you count these nodes, and then you follow it to the next node via this it becomes it.next assignment. And the crucial point here is that via strict funcs we tell the compiler that parameters are now deeply immutable, right? So the compiler is fine with this code, and it's also fine with these examples. So I want to insert something. It's a func. That means I want to be very, very strict about my mutabilities. But I say, hey, I want to append to x, which is a sequence of nodes. So X is mutable, is explicitly mutable via this var keyword, and Y isn't. So X can be like, I can say X set length, the old length plus 1, and then override what's in there. So this is a fine. And finally, I can also still mutate local state. So I have a variable of type node, but freshly created. And then I mutate it and set the data field. And since it's not connected to the n, the compiler is happy. So the semantics are, you cannot mutate what is reachable via parameters unless these parameters are explicitly marked as var. So here would be an example where the compiler says, yeah, look, no, you're trying to mutate m, so this is a type, it should be n. You're trying to mutate the object n, but you are in the strict func mode and it's a func, so you are not allowed to do that. And we can now play these games and see how smart the compiler is. So here I try to trick it into accepting the code, and I couldn't. So I select I have a helper function called select, which takes 2 nodes and returns simply the second node. And then I say, okay, I want to mutate n, but I assign it to it. So and then the it to y to x, then the x to y, and the y to z. And then I select either x or z, and then mutate the data field and overwrite the string to this value tricky. And the compiler will tell you, arrow an object reachable from n is potentially mutated. This line is where the mutation happens. And this is the statement that connects the graph to this parameter. So what it does internally is it has the notion of an abstract graph, and it starts with, hey, every graph that is constructed is disjoint. But depending on the body of your function, these disjoint graphs can be connected. And then when you mutate something and and the graph is mutated and it is connected to an input parameter, the compiler will complain. So the second rule, if the compiler cannot reason about the code, neither can the programmer. We really want a smart compiler helping you out because programming is quite hard. Another rule that is kind of famous, I think, by now is copying bad design is not good design. So if you say, hey, language X has feature F, let's have that too. This is just, okay, so you copy this design, but you do not know if it's good or bad because you didn't start from first principles. So, hey, C++ has compile time function evaluation, let's have that too. This is not a reason for adding compile time function evaluation to NIM. The reason why we have it, and we do it very differently from C++, is the following. We have many use cases for feature F. In this case, F is NIM's macro system, because we need to be able to do logging, lazy evaluation, type safe printf statement, and maybe a declarative UI description language, async and parallel programming constructs. So instead of building all these features into the language directly, we want to have a macro system so that we can add them without touching the compiler. Okay, and let's have a look at these meta programming features. So NIM offers templates and macros for this purpose. A template is a simple substitution mechanism. Here I define a template, which kind of, you can read it kind of like a function, but the crucial difference is that it expands the code directly in line where you have written this lock invocation. So you can compare this to the C code here where the lock is a define. It's quite similar. And then the reason why this is a template or a define is that we want this message parameter to be evaluated lazily. because in this example, I do perform expensive operations like string concatenations and turning variables into strings. And if debug is disabled, this code shouldn't be run. But the usual argument passing semantics are, hey, evaluate this expression and then call the function. And then inside the function, you would notice that debug is disabled and that you don't need all this information, so it doesn't have to be computed at all. And this is what this template achieves here for us. So because it's expanded directly in line 5, if debug is false, then this complex expression of concats and toString operations isn't performed at all. You can use templates for control flow abstractions. I've already mentioned, like we want a with lock statement. C# offers it as a language primitive in Nim, no problem. Like you don't have to build this into the language at all. Just write a template with lock that acquires the lock, and finally releases the lock, and in between them the full body is run that can be passed to this with lock statement via this colon indentation syntax here in line 9 and 10. You can use macros to implement DSLs. So here is a DSL for describing HTML code. So here the title is then of Nim, and the body is a bunch of rules that make no sense. Okay, and you can use metaprogramming for these lifting operations that come up again and again in programming. So for example, we have square root in math, we have square root for floating point numbers. And now I want to have a square root operation that works for a list of floating point numbers. And of course I could use this map call, but I can also create a dedicated square root function that takes in a list, in this case open array of t in line 4, and returning a new sequence of t, and apply every element of x is applied this function name f in line 7 that we pass to the template. In this case it's square root, and the final proc name is also square root because it's the template parameter name here used in line 4. So, and then you have a lifting. You can lift square root to lists or square or whatever operation you can come up with. You can use these templates to turn imperative code into declarative code. Here I have an example extracted from our test suite. So there are threading tests called tactors2, and thread example. And every single of these tests runs in 3 configurations, namely with the default options in line 5, with the default options plus the release switch in line 7, and with the options plus the thread local storage emulation in line 9. And so these test spec calls and make tests, they take many parameters like the category and the options and the file name, which is just distracting when you copy and paste it over and over again. So here we want to say, hey, I have a test, it's called tactors. I have a test, it's called tactors2. I have a test, it's called threadx. And by shortening this to the abstract, you are now working on the level of abstraction that you actually want to work on. And now you can shorten this further because you want to say, look, all these test invocations are kind of annoying. What I really want is to say, hey, test, and then I have a tactors test, tactors2, threadx. And you can use a macro for that. So here I have a simple macro that accomplishes that. And since it's so simple, it doesn't accomplish the full thing, but you need to be able, you need to say in line 9, apply this test call, this test proc, or in fact it's a template. Apply this test template to tactors2, and threadx. And this macro performs it by producing a list of statements, and every statement inside this list is actually a call expression calling this test, and the A is just the the current argument, that because we iterate over every argument in line 6. So the details are not really that important, but the crucial insight here is that Nim gives you the capabilities of doing these things, and it's once you get used to it, it's quite it's remarkably easy. Okay, next example, macro system to give us a type safe printf. Same thing, really. We create a statement list in line 9, we iterate over every argument, we produce a function call called write, and here I bind sim the write, but it's not a single write, it's an overloaded write operation, because I have 3 write operations. In line 1, 2, and 3, I define write for int, bool, and floats. And then overloading resolution kicks in and selects the write operation. And finally, in the statement list, there should be a call to this write new line function, which is declared in line 5 and just produces this echo new line. So another rule is, yes, the compiler is smart, but don't get in the programmer's way. We have a tremendous amount of code written in C++ and C and JavaScript that programmers really need to reuse. You cannot rewrite the whole world. And we accomplish this interoperability by compiling Nim to these languages. However, this is for interoperability. So the philosophy is not, hey, there is this code over there, and so the philosophy is not, let's use language C++ plus Nim because Nim doesn't offer some features that are required to get the job done. So Nim does offer bit twiddling and unsafe type conversions via cars and raw pointers and these low-level features, because you shouldn't. It's like interfacing with C++ is the last resort. Like usually we want you to write Nim code and only Nim code. But then the real world kicks in and says, hey, there's a bunch of code already written in these languages. How about we make the interoperability with these systems very good? So it's not so that we want to be Nim just one language out of many, and then you use many different programming languages to accomplish your system. It's ideally you only use the Nim language, because that's much cheaper to do. Like then you can hire other programmers that only know a single programming language rather than 4 or whatever you need. So yeah. This interoperability story goes so far that we actually offer an emit statement where you can directly put foreign code into your Nim code, and the compiler merges these things together in the final file. So here I have an example. You can emit a C variable, static int of value 420 in line 2, and the communication is two-way. So you can say, hey, I emit this fprintf statement, but the variable is actually coming from Nim, and this emit, like if you use these bracket notations, you can have both strings and Nim expressions and in the same environment, and so the C code can use Nim code and vice versa. However, this is really not a good way to do this interfacing. It's just showing that we want you to be able to get things done. There are much better way for interoperability, where you actually tell Nim, hey, there is an fprintf function here, it's coming from C, these are its types, I want to be able to call it, and this is the much better idea to do this. But this emit pragma gets the point very well across, that how we want the language to be practical. Okay, now a different topic. So far we didn't talk about memory management. In the newer Nim versions, it's based on destructors. called gcarg or gcarg mode. And so destructors and ownership are quite hopefully familiar notions from C++ or Rust. So a sync parameter in line 1 means the function f takes the string by owner, and it gets ownership of the string. And then it doesn't do anything with this x. So the question is, okay, did I produce a memory leak? What happens? And you can ask the nim compiler to say, hey, expand this function f for me, expand arg, like show me where the destructor calls are, show me where moves are performed, show me where deep copies are performed. And the compiler would then tell you, look, function f is actually your discard statement, and I added the call to the destructor here in line 3. And the nice thing is that you are still, like the nim's intermediate representation here for destructor injections, etc., is the nim language itself. So yes, nim is this one language that can express everything really well. Here I have a different example. So now I take the ownership of x, I really do something with the ownership, namely I put it into this global variable called g. And again, we can ask the compiler, what does it do? And the compiler says, yes, this is a move operation called equality sync. So we move the x into the g, and the move takes care of freeing what's inside the g if there is something, and then taking x's value over. And what it really did, and unfortunately that's not really visible here, is that it says, okay, x is moved into g, and then we say x was moved, so disarm its destructor and then call the destructor. But these was moved and destroy calls, they cancel out, and so the nim compiler optimized this out for us. And you can use these moves and destructors and copy assignments to create custom data structures. Here I have a short example, but I won't go into much detail. So the point is, destructors and move as operators can be written by you for your custom containers, and then they work well with NIM's other built-in containers, and it gives you a very precise control over the memory allocations and how it's done. So another Zen rule is, another Zen rule is customizable memory management. NIM is about customizable memory management. And since this is almost a complete statement, we know it's a rule of NIM's Zen. So, and finally, here are the rules once again as a summary. So copying bad design is not good design. We want to create good design by reasoning from first principles about the problem. If the compiler cannot reason about the code, neither can the programmer. However, don't get in the programmer's way. Like, the compiler is a smart dog, right? You can teach it new tricks. It really helps you out. It can perform tasks for you, like carrying a newspaper. But in the end, the programmer still is smarter than the compiler. We want to move work to compile time because programs are run way more often than they are compiled. We want customizable memory management. And concise code is not in conflict with readability. It enables readability. There was this rule of Zen, which was like leverage metaprogramming to keep the language small. However, it's hard to say that and keep a straight face when NIM really offers quite a lot of features. So there is a friction between we want the language to be complete and we want the language to be minimal. And NIM is more the older NIM gets, the more NIM is about we want the language to be complete. The minimal languages all grow to serve certain needs, and so yeah. Optimization is specialization. I haven't talked about this yet, but when you need more speed, you should really consider to write custom code. The NIM standard library cannot offer everything to everybody, and for us, it's also, and it's much harder for us to give you the best library for anything, because the best library must be general purpose. It must be the fastest library. It must have the least amount of overhead for your compile times. And that's very, very hard to accomplish. What's much easier is just to say, okay, Nim offers this as a standard library, but here I wrote this myself in 10 lines and I can benchmark it. And usually my custom code is faster. Why is that? Because it's hand-tailored for the application that I'm writing. So it's really like specialize your code and then it will run fast. That's really how it really works. And finally, there should be one and only one programming language for everything. That language is Nim. Thank you for your attention.